This video is going to be about the relationship between free energy and the equilibrium constant K. Okay, so what we know from previous material is that we can get the delta G from this relationship right here, as well as this one right here. And so if we find that the delta G is negative or less than 0, the reaction is spontaneous in the forward direction. And if you flip a reaction because of Hess's law, the sign changes. So it would be non-spontaneous because it would be positive if we flipped it in the reverse direction. And same thing goes for if delta G is positive, it's non-spontaneous going forward, but it is spontaneous going backward. All right, so this is the equation to get back and forth between delta G naught and the natural log of K. And so R is the universal gas constant. And the value that we use for that, because we need joules for energy, is 8.314, and it has the units joules per mole Kelvin. Okay, and so temperature has to be in Kelvin here. And remember, K's are unitless, and so it's just the natural log of K. It's just a button on your calculator. It's the natural log button. And delta G would then have to be in joules in this equation because our R is in joules. So if delta G is negative, then what does that say about K? Well, if delta G is negative, then that means it's spontaneous going forward. And remember, with K's, K is made, so if this is A and this is B, then the K would be found from the concentration of B over A. And so if it's spontaneous going forward, then that means we should have more B than A at equilibrium. And so therefore your K is going to be big because you'd have more product, so you'd have more numerator. If delta G is positive or greater than 0, then that means that the reaction is spontaneous going in reverse. So looking at the same fake expression here, we would still have B over A, but this time we would have more A because the reaction is going backwards. So that means your K is going to be small. So let's take a look at this. All right, first it says we want to calculate delta G naught and K at 298 for this reaction. So here's my free energies of formation for the reaction above. And so to calculate delta G, I'm just going to take the products minus the reactants times their coefficients. So I have 2 times negative 229 minus negative 300 plus 2 times negative 34. And I end up getting negative 90 kilojoules per mole of reaction. And so that's delta G naught. And then for K, the delta G naught is equal to negative RT natural log K. So I'm going to plug this in here, but remember I have to put this into joules, and so that's negative 90,000 joules. My R is 8.314 joules per mole Kelvin, and 298 Kelvin is my temperature. And then the natural log of K is what I'm looking for. All right, so the K's go away, and then I'm going to divide both sides by negative 8.314 and 298. So if I bring this over here, I get 36.33 is equal to the natural log of K. So to undo a natural log, if you look at your calculator, it's going to be the second button and then the natural log button, and that's E. So that gets rid of that. So I'm going to take E to the 36.33 power, and that is going to give me that K is equal to 6.00 times 10 to the 15th. So that's huge. That is a huge K, and it's because this is very spontaneous in the forward direction because delta G is negative. So this reaction is going forward a lot. We're making lots of product here. Okay, so example 2, cells use the hydrolysis of adenosine triphosphate, abbreviated ATP, as a source of energy. Symbolically, this reaction can be written as this. So we have ATP going to ADP, which is adenosine diphosphate because it's lost a phosphate. For this reaction, delta G is negative 30.5 kilojoules per mole. We want to calculate K at 25 degrees Celsius. So 25 degrees Celsius is 298 Kelvin. And my relationship, delta G is equal to negative RT natural log K. And I'm going to convert this to negative 30,500 joules. So I'll divide both sides by negative 8.314 and 298. And I get 12.31. Get rid of natural log by using E. My K is 2.22 times 10 to the 5th. So even though it's not quite as big as the last problem, it's still pretty large, and that's because we have such a negative delta G value, right? So negative delta G, big K, spontaneous in the forward direction. Part B says if all the free energy from the metabolism of glucose goes into forming ATP from ADP, how many ATP molecules can be produced for every molecule of glucose? So I'm going to find the delta G for this reaction, and then I can figure out how much energy I'm getting from that. So it's going to be 6 times negative 237 plus 6 times negative 394 minus negative 911, and that gives me negative 2875 kilojoules per mole of reaction. Now I know that this reaction gives me this much, so if all of this energy that I just calculated right here is going into this, right? And every single time we do this one, I get an ADP, then all I have to do is divide by 30.5. And that would give me about 32. 31 if you want to get technical. It's not like you can do half a molecule. All right, and then this last question says we have N2 plus 3F2 goes to 2NF3. We have an equilibrium mixture, and we want to calculate delta G. And we're doing this at 800 Kelvin. So my partial pressures, these are at equilibrium, and so if they're at equilibrium, that means we can find K, and so K, P, is going to be equal to the partial pressure of NF3 squared divided by the partial pressure of nitrogen times the partial pressure of fluorine cubed. So if I plug all those in, I have 0.48 squared divided by 0.021 times 0.063 cubed. So that gives me 0.2304 divided by 5.25 times 10 to the negative 6. So my K is 43,877.47. So then to calculate delta G, I'm just going to plug it into this equation. And my R is negative 8.314. My temperature is 800 Kelvin, and the natural log of 43,877.47. So this is going to give me negative 71,095.7 joules, which is going to be negative 71.1 kilojoules per mole of reaction. So that's it. So all of the questions in this video had negative delta G's and large K's. If we had a positive delta G, you get a small k. So you can try it with this one if you wanted to. You could make this positive and solve for k and see what you'd get. You'd get a much smaller number. It would be less than 1. So that's pretty much it. All you have to do is remember that if you have a delta G that's less than 0, that means it's spontaneous going forward, and your k is going to be big. If you have a delta G greater than 0, it's non-spontaneous going forward, and so your k is going to be small.